Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Today we'll continue our work on our course, Deep Learning for Computer Vision. Our lecture today is lecture number 4, that we are going to deal with colors. What are the colors? What is a color image? What are the color spaces, color models, and so forth. So let's jump to our lecture and share our screen with you. So as you have seen, here we're going to talk about color image models and spaces. Now, the session guidelines are as you see here. We start with color perception and spectrum as a first step, first. Then we'll go to color definition and its attributes, and we'll define also what are the color spaces, the color types, models, etc. And next we'll talk about image classifications, the types of images, binary, grayscale, colored images, indexed images, and so forth. And within the tutorial, we'll have a lot of demos and examples. So let's jump to our first title. Let's start with a brainstorming. What is the color and what is the color perception? What we mean by color perception? What is the color in general? As you know that the human vision system is a very amazing prophet for humans from or God, from Allah. And in case of when dealing with images or when dealing with vision, the human color vision is very complex in general, if you can see that, in comprehending, capturing images and understanding what is the meaning of these images. This is done by the human vision system as a total in general, and it starts, of course, by the eyes, the optical nerve here, as you see here, and it will be interpreted or interpreted by the human brain, and as we will see next. If you look at our human vision system, you'll see that we have the following, let's say, components. Here we have, for example, as a start, we can talk about the eyes. We have two eyes connected via the optical nerve, as you see here as a cross. Then the optical nerve will send its information and signal into the brain, where the interpretation of the scene or the image that has been captured by the human eyes. Of course, here the process is very complicated. In its simplest form, we have light incident to the objects. The objects will be reflecting their light to the eyes. Here we have an optical signal or optical light. Then the light will be converted by the retina in the very complicated or complex eye, which is a transducer of the optical signal or optical light into electrical or neural signal that will be sent by the optical nerve to the brain, where we can capture and understand all these topics or these viewed scenes in nature in general. Okay. So what is the color spectrum? What do we mean by the color spectrum? As you know that the color in general, or it's a sort of wave or radio wave propagation or magnetic wave propagation. And if you look at the spectrum, if you see here, we can see that the spectrum is very wide. And in our case, we are going to deal with a very small part of this brain, of this, optical spectrum, which is here. If we spread or zoom on it, we can see that the human vision system can capture light between about 400 to 700 nanometers. And it's a very small range that we can capture or see any object having such wavelengths. This is very narrow bandwidth or range. Even it's very narrow, it's very useful for our daily life and for our activities and knowledge transfer, etc. If you look at the spectrum, you can see here other types like ultraviolet. You can see the X-ray. You can see the gamma ray range. It's for very high frequencies. Here we have the infrared below the red, then the microwave, FM, AM, etc. So when you look at the spectrum, you can see that the frequency is very large. So in this case, we are going to use instead of having the frequency in hertz, we are going to deal with the wavelength in lambda, which in our case it will be between 400 to 700 nanometers, as I have just mentioned. Okay, so in this range, we can see all objects. So what's a color? What do we mean by color? What is the color? In fact, the color is the brain's reaction to a specific visual stimulus. So there will be a sort of excitation by the optical light incident into the eyes, and the brain will react on this specific visual stimulus by visualizing or by comprehending the type or the details of the object or the scene in front of the eyes. If we look at the spectrum or at our system or the human vision system, as you hear, we have the wavelength in terms of, or in respect to the human sensitivity in terms of the wavelength. As you see here, we have a sort of overlapping between the different subbands. As you see here, we have a sort of reaction to the blue color in the human vision system, and there is another reaction to the red, to the green color, and to the red color range. Of course, here I'm not talking about a very specific frequency or specific light or wavelength or specific color. So as here we have overlaps. In these places we have overlaps. This overlap causes a lot of details that are redundant, so they are extra by the human vision system. However, this is how the human vision system is organized and is constructed, and it has its own advantages for capturing the images. So the color can be described by measuring its spectral power distribution. So when we have here the wavelength and we have the sensitivity, so it looks like that we are measuring the power spectral distribution. So, for example, at this point, at this, let's say 450 nanometers, we can capture maybe something very blue. The same thing for the green and for the red. And as you see that even the colors are existing in our lives, the real concept behind the color is not something like you can say it's not a fake. It's something psychological, because there is nothing colored in our lives, nothing, only but we have the wavelengths and the spectral power distribution of these wavelengths along the optical spectrum that we can see here. So this sort of system will give us an ability to get a large degree of redundancy, extra information, since the eyes of the retina samples the color. So we convert the color from light into neural signal or electrical actually, and this will be transmitted to the by the neural nerve to the optical neural nerve to the brain. And so we can see that nothing is colored in our lives. Our human vision system is very amazing in converting these wavelengths and these power values and power distribution into pleasant and beautiful color range. Let's start with some color attributes. What do we mean by the attributes? Let's see. A definition that, or maybe a notation that you can hear here or there, is the brightness. What is the brightness? It's the human sensation by which an area exhibits more or less light. So the higher the light incident to the eyes, the higher the brightness of the object. The hue. What is the hue? The hue is the human sensation according to which an area appears to be similar to one or to proportions of two. Let's understand this in another way. The hue is related, closely related to let's say, it's very close related to the color itself. So we have, for example, a red color. It has a specific hue. Now, if we go to the let's say to the orange color, it will get another hue, and the hue will be a sort of degree or an angle that represents the color itself. So this is the hue. Another definition is the colorfulness. What is the colorfulness? It's the human sensation according to which an area appears to exhibit more or less of its hue. So the colorfulness reflects the sensation of an area to have more or less hue, which means that this color, for example, is orange. For example, the title here it has an orange color. And the colorfulness of this color, we may get some orange that is still orange, but it's very strong orange. And this is reflected by the value of, or the measured value of the colorfulness on this image. What else? We can also define something called lightness. That is very closely related to the definition that we have just seen. What do you think? Which one? Colorfulness, hue, or let's go back to the slide, or brightness? Of course, to the brightness, because here we have it's the sensation of the brightness, again, relative to a reference white in the scene. The difference between the lightness and the brightness is it is relative to some color, which is the white color. Now, the white color is defined by what we call it by D65 point, and I think it's totally out of scope of this course. I just need to explain simply that the lightness is very related to the brightness, but the difference is that in the case of lightness, we are relating the color, the brightness to a specific color, which is the white in this case. The chroma is very closely related to the hue and the colorfulness. So the colorfulness is the same as the chroma. Instead of that, just with a small difference that it is given to a specific to a reference color white. The saturation, the colorfulness of an area relative to its brightness. So now, how much this color is deep, the depth of the color or the colorfulness of the color gives you the definition of the saturation, or what we mean by saturation. Let's go to and have a look on this link. I think it will be easier to understand and capture the idea behind these things. Okay. Here we have a specific color model, color format HSL. H stands for hue, S for saturation, and L for lightness. Now, as you see here, that when we vary, of course, the first one is the H, the second one is S, and the third one is L. Forget for the third one, we keep it as one. It stands for the A, or the a new value that is not considered here. Now, if we take, for example, this color red, as you see here, now by changing this hue, we are changing the color itself. So we are going from, as you see here, we are going from red to the green, to the blue, to the purple, etc. Then we go back to the green. So it looks like a circle between 0 degree and 360 degrees. This is the hue. So let's keep it somewhere in here. Now, if we go to the saturation, as you see here, this is a red color, okay? If we start with a very small value here for the saturation, you see that the color has been converted to grayscale, to gray value. Now, by increasing the saturation, we are increasing the colorfulness, or increasing the depth of the red. We still have the color red. There is no change on the color red. As you see here, as we go further and further, we are increasing the color to be deeper and to be with higher colorfulness. Now, if we change, if we keep, let's keep it somewhere at this here at the mid. Now, for the third component, which is the lightness. Now, the lightness means again the brightness. So, if we take a higher value of L, we get more whiter and whiter. So we still have the color red without changing the hue or the saturation, but we are adding, we are going further and going up to 100%, which is in this case the white color. We can repeat this for other things, like for example here for the blue or for the purple. Maybe we take the green. You see here, by taking somewhere in between, and we get this is the colorfulness as a high maximum. Here we have the lightness as maximum or as minimum. As by changing the value here, we get so the idea behind all these things that the hue represents somehow the color itself in degrees as an angle. It could be represented also using what we call it by the chrominance or the chroma, and it will be it depends on the system that is used in this case and the color model, as will be explained later. For the second component, the saturation, which is the colorfulness, as when you increase the depth or the value, you are increasing the depth or the colorfulness of this color. Specifically, in this case, maybe the red, the blue, sorry, the green or the red, etc. While the lightness, the brightness, is how much light is in this color, or how much light is portion of light in this sample. It could be very high, approaching the white color. So the lightness or the brightness are very related to each other by with a difference that in the case of the lightness, we are referring to a specific color, which is the white, in respect to the white color. I hope that this is a good introduction for understanding the idea behind these, let's say, definitions and attributes. So let's go now to the color space. What is the color space? Now, I want to represent the color using, or in images, in color images, using a locus or maybe a space that defines the type and the of this color. So the color space can be defined simply as a way of referring to a model that represents all the possible colors that can be produced by a particular output device. What is the meaning of this? So we try to combine all colors that can be captured by a specific device. This device could be a printer, could be a screen, could be a mobile screen, maybe it could be a camera, it could be also a robot eye, etc. In this case, all these things are used and are, it's very important for these systems or devices to have a specific or a way to refer to the color in order to define which color is which, and as a result, to define or to give to get an action or to obtain a specific reaction on the this color space. In fact, all color space can be derived from the RGB information. As we have seen before, that the human vision system has three main subbands, one for red, one for green, one for blue. So the combination of these colors give us the RGB. And these colors are called the primary colors. In fact, the colors are have a very wide range of different colors as a combination of the three types of subbands, R, G, and B. So the color space are all derived from this basic or primary color space, or let's say color model. We can now distinguish different types of let's say color spaces. It depends on the application that is used in your case. For example, here we have old versions of the color spaces, CIE. They are very compatible to the human eye or human vision system. The first one was called XYZ, then LAB, then LUV. Then we generated other color spaces, like we call it the primary or the secondary maybe. The primary is the RGB, the secondary is for printers, CMY or CMYK. We'll talk about this later on. And there are other artistic color models that are used in advertisements and in very advanced applications. This includes HSI, HSV, HSL, etc. All these color models are useful for specific applications. So they are application based. They are application based. Now let's go to the RGB color space, the primary color model. Now the RGB color format was designed earlier for CRT tubes. If you remember that in the past we have, instead of the digital screens, we had CRT tubes where we have three guns, one for red, one for green, one for blue. This electron gun receives the electrical signal from maybe from the device and pushes the gun toward the phosphorus plane of the device and gives us specific colors. Now, on the screen, we have three colors. The combination of the three colors, when they are reflected to our eyes, they are interpreted in the space, and this will give us a full vision of all colors or the full brightness of the three primary colors. Now, we can also mention or say here that the RGB color space is additive. What do we mean by additive? We start with black and go up until we add all colors up to getting the white. Before looking at these specifically or these cubes, let's have a look, a simpler look. Let's say the following. Suppose that we have here the red. Let's have the blue, because they are the colors are primary colors, so they are perpendicular to each other. And we want now to define a specific color at some point in space here. So now what we are going to do, we need to project, to have three projections. So we have the first projection is on the R axis, the other one will be on this axis, and the other one will be on this axis. So we have three values. One is the green value, sorry, the here not green. Here we have the, let's say, the red. Here we have, as you see from the color, here we have this component will be the green value, and here we have the blue value. Now this is a vector, actually. This is a vector having these three components. So we have, let's say, this vector as P at location XY in space. It will be represented using three, we call it triplet, three color components, R value, G, and B values. We call this as a color triplet. Okay. Now, how we can construct all colors and combine all received or perceptible colors into a color space? How we can do this? We can combine this in a cube. Starting from 0, this is the point 0, 0, 0, and up to reaching some value, which is the white color, as will be seen in a better illustration on the slide itself. So the color triplet represents the three components of each pixel, colored pixel, or color stimulus, let's say, and that can be captured or maybe produced by a specific device. Okay, let's zoom this piece of. If you look at the white color and the cube, here as we told you, here we have a cube. If we take this in form of discrete version, we start by some value inside the cube down there, 0, 0, 0, somewhere in here. It's not seen from this location. And this is the maximum value, where we have maximum for what? As you see that we have different positioning for the colors. This is no problem. You can rotate the cube. So the maximum value in G will be 255, for R 255, and the same thing for blue. So all these combinations, if you take equal values of R, G, and B as a maximum value, you'll take the color triplet to 55, 255, 255. This will give us R, G, and B as maximum, and the combination will give us the white color. Okay, this is the color cube, or the RGB color cube. We call it the RGB color cube. You can see also on the same slide, there are, when you go back to your to the student booklet that I provided you before, you can see there are also other details here. For example, we have another color, pixel. This pixel has the following values. Here we have this pixel, okay? So here we have R, for R, we get 83, G 150, and B 60. So in all colors can be represented using the RGB color cube. So it's additive because we start from 0 with no color and rising up to to the maximum and floating inside this cube. And this point represents the vector that is representing the color triplet or representing the pixel at this location. Okay. Maybe we have a look. Let's go back on this part. Maybe it would be much better. Yeah. If you look at this cube again, you can easily understand and see that we have here all colors are clearly seen with zero, with zero, with zero, 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 zero black, and with 111 or 255, 255, 255 here normalized to max as 1. And the diagonal here, the diagonal that has equal values for where we have, in this case, R equals G equals B, this will give us this vector, this one, the red one, represents all equal colors from all components. And in this case, we are dealing with, let's say, the grayscale version where we have no hue and we have just the brightness, and all colors are mixed together to give the grayscale version starting from 0 black up to step by step up, rising up to 1 or the white. Of course, 1 in this case is normalized and symbolic representation for the color itself in case of the white. Okay. Okay. Let's go further. Another format is called, or the color space, we can call it the CMYK. As you see here from the colors of the letters in here, C cyan and magenta, yellow for Y, and K for black. Here, usually this color space or color model can be used in case of printing applications. Why we need for printing such a color space? As you see here, the color cube, if we have a look at, let's zoom this slide a little bit. Okay. If you look at the, let's say, take the one in the middle. So it's very clear here that the red here, blue, and green. It looks like that the color cube has been inverted upside down. And the main vectors or main planes having the yellow, the cyan, and the magenta. In this case, we start by a value of 0, 0, 0 for the white, while the maximum value will be for the black. What's the idea behind this? Why we need to invert this color cube? This color cube represents the CMY model or CMY color space that is called as or denoted as subtractive. Why subtractive? Because we start by the white and go up to get the black. What do you think? Where we have such an application that requires the start to be white and goes up to black? In screens and digital displays, display usually when it is shut down or no input, we get a black background, a black color or a black screen. It's clear that when we add colors, we add components, we get go up to the white color. While in case of the CMY cube, we start from white. Where do you think we need to start from white? It's very clear and very simple to go and simply think this will be in case of printing devices where we have a white color or a white paper. And in this case, we need to start with the white instead of starting with the black. As here we have the RGB components. The intersection between R and B gives us the cyan. The intersection between green and red gives us the yellow. And the intersection between the G and B gives us the the cyan, yes. And here we have the magenta. Now, where is the black? Where is the K? Where is the K value here? This K is missing. Actually, this K is used for grayscale printing. Grayscale printing, okay? For grayscale printing. What we mean by that? Usually we have, let's say, a printer. We have two cartridges or two color banks. One for color printing, where we have color images, color fonts, etc. And when we have black and white text, you need to print using a black and white or grayscale cartridge or color bank. In this case, we use the K as a sort of grayscale printing when we have in our document a lot of color, let's say, color images and text, etc. So finally, we can say that the CMYK standard is a subtractive color model because it starts from white and goes back up to the black. Let's have an example. Here we have this one here. Suppose that we have here we have four 2x2 image segment as here. It's an RGB. We sometimes refer to the Adobe corporation because it's a very strong and very well-known corporation in this field. This image segment, it's a piece of 2x2 pixels only, having these components for the RGB. For example, the first upper left corner pixel, 25, 23, and 19, etc. So we have different values for the colors here. We have four components, four pixels, four color types. You can call it as you want. And it's required to find the corresponding CMY values for the same image segment. How to solve this? We have a simple matrix. As we have just said, it's a subtractive color. It's on opposite to RGB. Having RGB, so having this RGB, here as you see, we have RGB. We want to find the CMYK as a result. We just need to apply this matrix subtraction. Okay, and let's see what will happen here. We'll get. So these are the CMYK components in case of having the three color, the 2x2 color segment having three color triplets. Okay. Next, let's see what we can do also. Another example having the same color, the same segment, 2x2 segment, it's required to find, or it's asked to find the YUV. What is YUV? In fact, YUV is a color space that was used in TV applications, where we have like YUV and YIQ, where we have in-phase and out-of-phase components. In case, just to remind you, or just to let you know, when we have YUV, the Y represents the brightness, okay. U and V are the color differences, or we can call it the chrominance components. So instead of transmitting the RGB color, which is redundant, there was a method or a tool to compress and reduce the number of bits required, or number of the channel size or the bandwidth required for transmitting three similar color channels, R, G, and B. We just concentrate on the Y, the grayscale version of the image, and we just apply U and V color differences that are used as a sort of replenishment. So you take the image as being grayscale, then you try to colorize this image by adding some replenishment, which is represented using the U and V components. Now, all these color types and color models can be found and can or you can find for it the conversion matrices in books and on the net. For example, this one, to get YUV, you need just to apply this matrix multiplication. In this case, you have to remember that to find Y, we need to multiply this row by this column. As you see here, Y equals, okay, Y equals 0.299 R plus 0.587 G plus 0.114. In fact, these numbers were selected experimentally, and it was for a long time, maybe about 50 years old now, to get the brightness or the lightness of the grayscale version of the image. While for the other components, here, as you see here, for the U and V, we need just to multiply this row by this column, this row again by this column to get the U and V respectively. So this matrix multiplication helps us to find out the YUV color triplet from RGB. And when we have the opposite operation, by having an opposite matrix to this one, and if we call this as M, we may find an inverse matrix, which is M inverse, to get the opposite action on the other side. Because finally, what we see the RGB. And what we transmit, what we may record or may save, it could be YUV, YIQ, etc. All these things are also available and are very useful in compressing the size and the bandwidth required for transmitting very wide or very wide range of color components, especially when we deal with videos and movies. And this is our final answer for these values, as you hear. So another look, if you look at the values for U and V, for example, this one, for this one, for this one, and for this one, you see that we have fractions, we have negative values, because these are color differences. They are chrominance components. So they have specific meanings for sure, but for vision, doesn't mean anything for us. It's just a sort of compression to get lower and narrower bandwidth. Okay, the same thing is true for the V component for the 2x2 image segment. Let's go to a very important color space. It is called YCBCR or YCRCB. In fact, this color space was invented when we deal with digital images. It was maybe maybe 20 or more or less years ago. In the YCBCR or YCRCB, is very widely used in digital videos. This format, as here, it's moving. When we have the CB component that is now going away, and this one for the CR, as here, this is the chrominance for the red, this is the chrominance for the blue, and this is Y. The again, Y is the grayscale version of the image. When removing CB and CR, you get a grayscale image without colors. If you look at the image here below, let's have a zoom a little bit. Here it looks that we can use a digital camera. We call it CCD, which is a charge coupled device. This camera is available everywhere in your mobile phones, in your computers, etc. Now we have this image, colored image, and we take inside this the charge coupled devices 3 types: one for the red, one for green, one for blue. So usually we capture the image using the RGB color format or color space. Next, we convert into the YCRCB. There is a lot of formats of the YCRCB. You can find it on the net and in the booklet for the tutorial where you can see how to convert from RGB to YCBCR or YCRCB and different versions of it. Now, as you see here, the Y component represents the grayscale version of the image here. As here, from here and here, you can see the difference that this is only the grayscale version. While CR, it contains the color difference for the red, and this is the color difference for the blue. Now, what is the meaning of this? Again, it's just for compression and to reduce the size and the bandwidth required for transmission, or even for storing or saving such videos or images. Okay. This is the YCBCR cube. Here it's moving, here it's just steady to see the idea behind. It looks like the RGB cube, but with some sort of rotation to get specific these specific components. Let's have a demo. Here we have the RGB. This is for my lovely city Jerash, from the ancient old city in Jerash. It's part of the ruins in Jerash here. As here we have an RGB image, colored image. Now we can split into three components, RG and B components. As you see that the image has a lot of redundancy, we can see that there's a repetition or extra information that can be discarded somehow to reduce the size and to get a compact version. Now, when we go to the YIQ color model, it's again like YUV, YIQ. If we split even YCBCR, as we have seen, if you look at these components, you can see that the Y component, which is the grayscale version, while the I and Q components are, let's say, chrominance components or difference color components, and they contain more or less some info. I hope that it will be seen on the video. Here, the I component has more details than the Q, maybe specifically for this image, but of course, for other images, it will be something different. It depends on the content of the image itself and how it can be interpreted and how it can be converted into these components. Now, a very good question is why we need a lot of color spaces. Of course, you know that all over the world, people are working, are inventing, are producing devices, and every company or every country may produce its own color spaces that fit with its own devices. And this is the main answer on such a question. Let's see what we mean by this. Now, when we have different color spaces, sometimes some color space is useful for example, RGB is good for video cameras, for movies, etc. But it's not very useful because it's not very compact. So sometimes we need another components, other color spaces that can be used for other purposes. Some color spaces are perceptually linear, like the RGB. Others are not linear. Specifically when we deal with computer graphics, they are always not linear in general. Some color spaces are intuitive to use, i.e. it's easy for them to be navigated and understand what's going on, how to change the color. Now, when you look at the RGB, you can see what is the difference. Now, when you go to the YCBCR or YUV, YIQ, you will see that something confusing. You can't get exactly directly from the components how these colors can be perceived. And this is why we may use different color spaces according to the application. As I just mentioned, that color spaces are tied to a specific piece of equipment. For example, if you have a printer, it may require some specific colors, I see MYK. If you have maybe a satellite telescope or something like that, you need to have another type of piece of equipment and other sort of color spaces. And this is why we need such a lot of variations in color spaces. This is just an introduction about the topic regarding this issue. So let's stop at this point and see you on the next part of this lecture.